Okay, so to finish off our section on equations, we've got a topic here that seems a little bit left field. It's called partial fractions. Interestingly, as part of partial fractions, we need to be able to solve simultaneous equations. So you can think of this, this is an application of simultaneous equations. But it's actually a technique, or I'll say a technique, that you end up using a little bit, not all that often, but you end up using it again in, I think, Math 1120, and then again in Math 2310. Okay, so you'll see it here, you'll forget it, you'll see it again in 1120, then you'll remember that you've actually seen it once, and then by the time you get to 2310, you'll actually have it mastered. That's my hope, okay? So here's your first exposure. So, partial fractions. Now, the idea of partial fractions is that it's the opposite of doing this. If I gave you here two algebraic fractions, to add them up, you would put them over a common denominator. Okay, we've done that before. So here I am, I'm putting them over a common denominator, then I'm expanding out the brackets and I collect like terms, and I end up with that addition of two fractions gives me this single rational expression in there. What partial fractions is going to do is we're going to start here and end up there. No, it's fun. Honest, we'll enjoy it. I enjoy it. Okay. All right, but that's what we're going to do, all right? So adding algebraic fractions starts on the left-hand side, ends on the right-hand side. We're going to start on the right-hand side and end up on the left-hand side. I mean, conceptually that makes sense, doesn't it? We're just undoing this. All right. So let's, and look, to make us sound like we're really smart, we're going to call it decomposition into partial fractions. All right. If you say that, you sound smart, I think. Okay. So here we are. So the kind of question you would get would be, decompose via partial fractions. And that sounds pretty scary straight away, but we understand it means I want to write this as the sum of two smaller algebraic expressions. So, let's have a go. The first thing to do is look at the denominator. Go back up here. See here, I had x squared minus 2x. I factorised that into x and x minus 2. So here, I need to factorise the denominator. That's going to be my first step. So let's do that. So I'll say, factorise x squared minus x minus 12. And in this case, that's hopefully doable because we're getting good at factorising quadratic trinomials now. And I see that as being x minus 4, x plus 3. Minus 12, minus 4. Yep, that works. Sitting there. So I've factorised the denominator. Now what I want to do is I want to write this expression as the sum of two other expressions with these as its denominator. So what I want to do, now we want 2x plus 1 over x squared minus x minus 12. I want it to be some number over x minus 4 plus some other number over x plus 3. And my job now is to find the a and the b. So in this case up here, this would be 2 on x and 3 on x minus 2. So it would be the equivalent of finding a is equal to 2 and b is equal to 3. That's my task. And to do that, begin by multiplying both sides by the denominator here. So multiply both sides by x squared minus x minus 12. Now, I'm going to put in some L-plater steps in here. You don't have to do these, right? If you want to skip these, by all means do so. But if I'm multiplying both sides, x squared minus x minus 12, then I would have this on the left-hand side, x squared minus x minus 12, agreed. And on the right-hand side, I'm not going to write it as x squared minus x minus 12. I'm going to write it as x minus 4 times x minus 3 times a over x minus 4 plus b over x plus 3. Right? What I do to the left-hand side, I have to do to the entire right-hand side. That number is equal to that number, so if I multiply by x squared minus x minus 12 there, I've got to multiply by x squared minus x minus 12 there. Now on the left-hand side you can see that they will cancel out. So on the left-hand side I will just have 2x plus 1. On the right-hand side, here I've got multiplying by x minus 4 and I'm dividing by x minus 4, so I'll be left with just x minus 3. So my first term there will be a lots of x minus 3. And over here I'm multiplying, whoops, I've got the wrong one there, that must be plus 3, sorry. I've multiplied by x plus 3 and I've divided by x plus 3. So this will leave me with b lots of x minus 4. Yo. Sorry? Oh, yeah, tough. Once you get going, you'd be able to go straight from there to there without writing out these interim steps. Okay, but for the minute, if you need to, write out the whole lot. So now we're in a position where we can find the A's and the B's. And again, I noticed the notes has two methods and has given them two different names. So let me do the same. So I'll say here, method 1 will be, I think the notes call this the method of undetermined coefficients, which again makes it sound really difficult, but I don't think it is. Maybe it is. In the assessment task, do it by whatever method you can, whichever one you find easiest. But in the method of undetermined coefficients, what we do is we multiply or we expand out the grouping symbols here on the right-hand side. So when I do that, I have 2x plus 1 is ax plus 3 times a plus bx minus 4 times b. I then collect like terms. And so here I'll have a plus b x plus 3a minus 4b. I then say to myself, I might even write this as 2x plus 1 there. On the left-hand side here I have an expression 2x plus 1. On the right-hand side I have the expression a plus bx plus 3a minus 4b. If these expressions are going to be the same for all values of x, then the coefficients have to be the same. So in other words, a plus b has to be 2 and 3a minus 4b has to be 1. So I can say here, equating coefficients. Equating coefficients, I have A plus B is equal to 2, 3A minus 4B is equal to 1. Have a look at this. I need to find A and B. This is a linear equation in A and B. This is a linear equation in A and B. So that's a set of simultaneous equations in A and B. And wacko, I already know how to solve them. Okay? So here I go. I'll just say, by magic, solve simultaneously. I'll leave out all the steps. Solve simultaneously. And you do, when you do that, you find A is equal to 9 on 7. And B is equal to 5 on 7. So as you can imagine, there's a few steps involved in there. In this case, I would probably do a substitution method. I'd make B the subject and substitute in. Okay? But in concept, you can do that. So now let me show you method 2. Look, the reason, as I think about it, that we've shown you two methods is method 2 is way quicker in all the examples I'm going to give you in this course, but when we get into the other courses, method 1 turns out to be better. Okay? But certainly in this course, method 2 seems to be the better one. So here we go. Method 2. Has it got a name? I can't remember. Yep. Just to confuse you, it's called substitution method. So you've seen two substitution methods. One refers to a simultaneous equation, one's referring to partial fractions. But will that confuse you? No, you're wise and clever. Maybe, okay? But let's go back to the equation. I'll write it again because we can't see it. But actually we can see it, I'll put it here. Go back to this equation here. We're trying to find A and B in here. Now, I said to you, this expression on the left has to equal the expression on the right for all values of x. As a result, the coefficients have to be the same. Another way of thinking is saying, this expression on the left has to be equal to the expression on the right for all values of x. So if I put x equal to 4, it must be true then for a particular value for x. Why x equal to 4? Well, let's have a look. So I shall put x equal to 4 into, and I better give it a, let me call that equation 1 just so that we know what I'm talking to. If I call that equation 1, if I put x equal to 4 into equation 1, then on the left-hand side I have 2 times 4 plus 1. On the right-hand side I have A, and now that's 4 plus 3, plus B, and now I have 4 minus 4. And the beauty of that is 4 minus 4 is 0, that term disappears. So I have here 9 is equal to 7A, so A is equal to 9 on 7, which is neat and quick. So what would be another good choice of x, would you suspect, sitting over here? I can use any value of x that I would like, but there are some choices that are better than the others. Now, I chose x equal to 4 from there, so the second choice for x looks to me like minus 3. Minus 3 would be a really good choice. So I'm going to put x equal to minus 3 into 1. And when I do, I get 2 times minus 3 plus 1 is equal to, and that's just going to be 0. And then I have b, and I've got minus 3 minus 4. And so that says minus 5 is equal to minus 7b. So b is equal to 5/7. And so once again, very quick, very neat. And even better still, it's got the same values that we got up there. So I can tell you now method 2, in all the examples you're going to get in this course, will always be quicker than method 1. Maddie?
Do you always use the switch sign, so like the -4 becomes +4 and then +3?
Yes, because that makes that bracket, when I substitute in, 0. Yeah, I want to choose the number that makes the bracket 0. Yep. And so what we have found out of all of that is, therefore, 2x plus 1 on x squared minus x minus 12 is equal to a 9/7 over x minus 4 plus 5/7, if you like, over x plus 3. And I guess I could write that as 9 over 7 lots of x minus 4 plus 5 over 7 lots of x plus 3. And that is my partial fraction decomposition, to use big words on you, okay? To use math speak, I call it. And the beauty of this, of course, is you can check your answer. You can check your answer by putting that over a common denominator and collecting like terms. So should you get the urge, you can check this. I don't have the urge, all right? But you certainly could do it.
So that last step where it was 7 bracket x minus 4 plus...
Here.
Is that the way you would
This one?
display it in the exam?
In the multiple guess thing?
Yeah.
I'm actually more likely to use this one, yes.
Yeah.
Yes. But I would hope that you've done things correctly and you've recognised the 9/7 and the 5/7, so you would actually recognise that. Okay, I hope. I mean, it would be a real pity, wouldn't it, to get down to here, get all these right, and then not recognise the right one out of the options. But that's the nature of multiple guess. Because sometimes you just guess it and you get it right, so what comes around goes around, I think. Okay, so let's do another one now. We're feeling good. So let's decompose this via partial fractions. So, firstly, the first thing to do is to say x squared plus x minus 6. We factorise that, and it looks like an x plus 3, x minus 2 jobby to me. Let me just check. X squared plus minus, yep, that'll work. Okay, so I've factorised the denominator. And so what I want is I want to write 5 over x squared plus x minus 6 as a over x plus 3 plus b over x minus 2. And my job is to find the a and the b. To find the a and the b, I'm going to multiply both sides by x squared plus x minus 6. So multiply both sides by x squared plus x minus 6. When I do that, on the left-hand side I get 5. On the right-hand side I'll get x minus 2 plus b lots of x plus 3. So there you go. I skipped all the steps in the middle there. I'm trying to make it look like it's really easy. Yes. I would like you to have the understanding rather than trying to just rote learn a method. But yes, what you say is true. Now, I'm going to use method 2, and I reckon a really good choice for x might be the value 2. Now, on the left-hand side, when I substitute x equal to 2, there's no x's there, so I just get 5. That's 0. So I have here 5b, so b is equal to 1. What's another good choice for x? Yeah, negative 3 is a really good choice. On the left-hand side, there's no x's in there, so I just get 5. And here I have a times minus 3 minus 2 is minus 5. That's 0. So that tells me a is equal to minus 1, and I'm done. So therefore, I'll say thus, because that makes you sound clever as well. X squared plus x minus 6 is equal to minus 1 on x plus 3 plus 1 on x minus 2.